And I'm the Director of Innovation Initiatives at QTRIC. Today's session will focus on hydrogen fuel cell alternative solutions and efficiencies for heavy duty and transit applications. Before beginning, we'd like to do our land acknowledgement. I'm currently located in Hamilton, Ontario, and in the spirit of respect, reciprocity, and truth, we honor and acknowledge the lands which constitute the present-day city of Hamilton, situated upon the traditional territories of the Erie, Neutral, Huron-Wendat, Haudenosaunee, and Mississauga. This land is covered by the Dish with One Spoon Wampum Belt Covenant, which was an agreement between the Haudenosaunee and the Anishinaabeg to share and care for the resources around the Great Lakes. We further acknowledge that this land is covered by the Between the Lakes Purchase 1792 between the Crown and the Mississaugas of the Credit First Nation. Today, the city of Hamilton is home to many Indigenous people across Turtle Island, and we recognize that we must do more to learn about the rich history of this land so that we can better understand our roles as residents, neighbors, partners, and caretakers. QTRIC encourages and supports Indigenous communities throughout a number of actions. We also have a gender and racial diversity policy in place that encourages the hiring of diverse voices, maintaining racial and diversity targets, as well as building organizational awareness and education therein. If we can move to the next slide. A few housekeeping items. Many are used to this already. You'll notice you have the mute and the video buttons to turn them off and to mute yourselves. There is the participant chat. Next slide, please. There's the participant chat, live transcript, reactions, and how to end your meeting. And clicking on the participants will show who's here today. Now, speaking of participants, you'll notice that a number of names will be listed as unknown. This is because of the system we are using. We and everyone else will want to see your name and your organization of those that are participating today. So if you could hover over the unknown, select the more, and then click rename. Please enter your name and organization and then hit save. That way we'll know who you are. And with that, I'd like to go to the next slide. And we'd like to acknowledge and thank our sponsors for this series. Thank you to Atura Power, Novabus, ABB eMobility, NFI, Centennial College, and Transport Canada. I'd like to now show you a couple of our sponsor videos.
The NovaBus battery electric bus sets the standard for durability and performance, no matter what type of weather comes its way. Driving across America, the LFSC Plus vehicle has demonstrated tremendous energy efficiency, strong gradability performance, a remarkable drivability, and an industry-leading turning radius. Hopping aboard the LFSC Plus means getting the support you need to facilitate your transition towards zero emission. Our experts are there to help you integrate the electric bus seamlessly into your operations. Choosing NovaBus also means selecting a highly talented team of training professionals and tailor-made programs to meet your needs. Hit the road with the confidence that comes from being supported by a wide service network that doesn't let you down. That means getting the specialized spare parts you need quickly and 24/7 customer support that is recognized for its agility and flexibility. NovaBus, your partner for a sustainable future.
So thank you, Novabus and ABB e-mobility. Now I'd like to just give a couple of comments on why we are here today. The QTRIC R&D Innovation Series is a 3-day webinar format event taking place. One was August 16th, today is September 12th, and the next one is October 3rd. The objectives of this series are to highlight key projects that were recently completed through QTRIC's coordination, which was sponsored by the Government of Ontario's $10 million fund as part of its climate change strategy. The goal of the partnership with the Ministry of Economic Development, Job Creation and Trade was to help move the province to the forefront of public transit research and development, supporting QTRIC's founding mission to spur innovation and economic growth through the creation of low carbon and smart mobility ecosystems. We further wanted to facilitate interaction between researchers and industry partners for future research collaboration opportunities and commercialization adoption. And all of this is to support low carbon and smart mobility ecosystems and the adoption in public transit by fostering innovative agendas and capacities. So the last session in August focused on bus electrification, which was battery charging, powertrain storage, and grid management. Today's session will focus on fuel cell alternative solutions and efficiencies for heavy duty and transit applications. And in October, we'll be talking about autonomous shuttles and monitoring transit satisfaction. Next slide, please. So our agenda today will basically run from about 2 to 3, or maybe the times aren't as important, but we will end at 4, and we will do a Q&A session at the end after all speakers have completed. So you're invited to submit any questions in the chat, and our staff will be monitoring them, and we'll make sure they get asked as time permitting. Next slide. I won't introduce the speakers. That will be done by Matthew Morrish, who is our MC for today. I will introduce Matthew. We won't be sharing bios. The bios are on the website. So for time efficiency, we're just going to introduce Matthew. Matthew will introduce the speakers as we go forward, and we'll take it from there. So I'd like to introduce Matthew Morrish. He's Business Development Manager for Hydrogen Atura Power. Matthew is the Business Development Manager for Atura Power based in Oakville, with over 10 years of diverse and progressive experience in financial market strategy, M&A, business development, energy, and hydrogen energy. He is dedicated to leading the carbonization of the energy sector to achieve net zero 2050. Matthew holds an MBA degree with distinction from Western University's Ivy School of Business. And with that, I'd like to introduce Matthew to the stage.
Fantastic. Thank you very much, Vince. And it's a pleasure to be here on behalf of QTRIC to moderate today's event on hydrogen fuel cell alternative solutions and efficiencies for heavy duty transit applications. I have to say, on a personal note, it is not hard. It's very hard not to be excited watching those introduction videos. And I think we're all in store for some great presentations today. A quick background on Atura Power, and we'll have a video here start shortly. But Atura Power is a subsidiary of OPG, and we own and operate the largest combined fleet of natural gas power plants, providing over 2,700 megawatts of peak power to the Ontario grid, which is enough to power about 2.7 million homes. Within that umbrella of Atura Power, we are also dedicated to developing new decarbonization technologies, including battery electric storage at the district scale, new gas opportunities, and my specialty, hydrogen. We have 2 facilities that we're advancing through to commercial production, predominantly as our Niagara Hydrogen facility, which will be online at the end of 2024, producing 2,000 tons per year of the lowest carbon intensity bulk tonnage supply of hydrogen available in Ontario. That will be followed with a second project at our Halton Hills facility in 2026. And our goal is to be able to produce low carbon intensity hydrogen in the amount of about 50,000 tons per year towards the end of this decade. And with that, I will pass it over to our video for a quick little introduction on Atura Power. Great, and we're on to our first speaker today. So without further ado, we will introduce Dr. Hani Farag, Associate Professor at the York Research Chair in Smart Energy Grids at York University. And his presentation today will be on the Decision Support Toolbox for Hydrogen Production in Ontario. Dr. Farag, off to you.
Thank you, Matthew. It's my pleasure to be here, and good afternoon, everyone. Give me just 1 sec to share my screen and I will be ready. All right, so Matthew, can you check if the screen is there?
Yep, we can see it.
All right, perfect. So again, good afternoon, everyone. My name is Hani Farag. I'm Associate Professor and York Research Chair in Integrated Smart Energy Grids at York University. The introductions that Matthew did, actually, it's a bit interesting. I remember back in 2016, I had a meeting with the business team at Hydrogenics before they got acquired by Cummins, and we were discussing how to come up with the potential integration of the electrolysis system so we could produce the green hydrogen that is needed to supply multiple kind of applications. And since then, I have been working on the development of innovative tools that could be utilized by business developers and also by operation managers to look into the techno-economic aspects for the integration of the green hydrogen plants using water electrolysis. So as you could see here in the screen, the project we have done with the QTRIC back in the days, we started in 2021, and then we concluded this study last year. The hypothesis of this study was focusing on the hydrogen production that is needed using the utility scale electrolysis to supply fuel cell electric bus in Ontario. The question was, if we go for 100% fuel cell electric bus adoption in the province, how much hydrogen do we need? And how can we potentially supply this hydrogen from the electricity system in Ontario? So as you could see here, this is a typical kind of schematic diagram that shows the entire system, where it does have the electrolysis as a key component in the green hydrogen production, interfaced via a rectifier that converts the AC into DC. And once the hydrogen is produced from the electrolyzer, then we definitely need to have some sort of storage to store hydrogen. Lots of research is investigating the mechanism of storing hydrogen, whether it is in the form of gaseous or compressed gas or liquefaction or liquid organic hydrogen carriers. And there might be also a need to have a transportation mechanism for hydrogen if we produce hydrogen offsite. And if we produce it on-site, then we might directly supply it to the hydrogen fueling stations. So this is an overview about the project we have done with the QTRIC in the past couple of years. First of all, we did start with a quick review for the state of the art for the different types of technologies that we currently have to A, produce hydrogen, and B, utilize hydrogen as well. And as I mentioned earlier, one of the key questions that we were trying to address in this research project is, how much estimated or projected hydrogen demand we might have if we go for 100% fuel cell electric buses. We do understand the fact that many transit operators are currently moving toward electrification of their transit fleets. And the number one technology that is currently under investigation is basically the battery electric buses. But we do also understand the fact that fuel cell electric buses might definitely be the counterpart of the battery electric buses at certain time once the technology is ready for implementation and deployment on a larger scale. So one of the key questions we also try to address is, if we are going to produce that amount of hydrogen to supply fuel cell electric buses, how are we going to produce this from the electricity system? In another word, should we go for more kind of centralized hydrogen generation plants, or should we go for a more kind of distributed on-site hydrogen generation plants close to the utilization? And as I mentioned, fuel cell electric buses versus battery electric buses, that is the dilemma that we currently everyone is working on and trying to investigate if both technologies could go hand in hand, or one will, take over the other one. Another important aspect we were trying to address in this project is we do understand the fact that from the economic perspective, hydrogen production is not ready yet. The target is hopefully at certain point to reach to a $1 per kilogram of hydrogen production in order to compete with other, I would say, non-green technologies, such as SMR process from natural gas and others. But we are far from that. And the key reason of this is basically because of the cost of the electricity. And despite the fact we noticed that there is a significant decline in the cost of producing electricity from renewables, energy storage technologies, etc., still, we are not on that stage where we claim that hydrogen is a cost-effective solution when it is produced from electricity. So one of the possible mechanisms to offset this cost, or at least to reduce the cost for hydrogen production, is the integration of such hydrogen generation plant with the electricity system. Have been working with ISO closely in terms of potential integration of hydrogen plant with electricity system in order to provide some sort of flexibility, dispatchability, and operability for the electricity system, something that is ISO is keen to have in the decarbonization pathways that they published in the recent report last year. And to do so, hydrogen generation plants need to provide services such as operating reserve, demand response, and other grid services that the ISO might demand for. All right, so just take you to some of the findings and analysis we have done throughout this project. As you could notice here from our survey, we do notice the fact that there are different types of different types of electrolysis technologies in the market. Alkaline, PEM, and high temperatures, they are in different stages in terms of the market availability. Alkaline is well matured, yet one of the key issues for alkaline is that it's not kind of a high dynamic, and consequently its potential integration with renewable intermittency is not going to be in favor of that technology. But it might work perfect for other applications, like when it is co-located, for instance, with nuclear power plants. PEM electrolysis, on the other hand, it's a technology that is currently available in the market, highly or potentially being deployed in the next few years. It has better efficiency compared to alkaline, and it could be potentially work well with the intermittency of renewable energy resources. High temperature, or SOC, it's a technology still under commercialization, and it is not that much scalable. One of the key aspects that we have considered in our calculations to come up with the techno-economic analysis needed to design the hydrogen plants that are going to supply fuel cell electric buses is how much electricity demand we need to produce 1 kilogram of hydrogen. And if you look into the manufactured sheets from different providers of electrolysis, you could figure out that this is in the range of 50 kilowatt hour per kilogram. CapEx cost is in the range of $550 per kilowatt. Water demand is not going to be an issue, especially in a country like Canada. If we look into the technologies for the electric fuel cell buses from Ballard, for instance, and other providers, we talk about a tank in the range of 40 to 50 kilograms of hydrogen. And in average, the energy consumption for those buses is about 0.1 kilogram per kilometer. So this is a basis that we could potentially look at when we think about running a techno-economic analysis and think about the optimal design for green hydrogen plants to supply fuel cell electric buses. So we looked into Kyoto handbook and we collected all the data needed from transit bus operators in the entire province, looking mainly into how much is a kilometer run from each transit network in a daily, monthly, and annually basis, just to quantify how much hydrogen do we need per day, per month, per year to look into that hypothetical scenario of 100% fuel cell electric bus adoption. And you could notice those numbers, for instance, 127 tons of hydrogen needed per day, 3,082 needed per month, and more than 46,000 of tons of hydrogen needed annually to run those buses. Now, from the electrical system perspective, which is the one that I focus on in my presentation, how do we map that hydrogen demand to the ISO zones? So what we did, basically, we looked into the different transit networks and where they are located and map them correctly with the ISO zones in order to determine the distribution of the hydrogen demand for each ISO zone. Unlike battery electric buses, where it's a plug and play, where you just plug with electricity. So if we do have 100% battery electric bus electrification in Ontario, so the demand of the buses will be local. But for hydrogen, it might be local if we do have local hydrogen production plants, or it might be not local if we go for more kind of centralized approaches. So we did the mapping for the hydrogen demand. We looked into two possible options, centralized versus distributed solutions for hydrogen production plants. So for the centralized hydrogen production plants, and this is a kind of detailed optimization models that we have developed in-house to come up with the optimal sizing and to determine the capital cost needed and operation cost needed for having those hydrogen generation plants supplying the fuel cell electric buses. So this table shows, for example, that if we have only one central plant in Ontario, we end up with having 550 megawatt or megavolt ampere of electrolysis plant needed. And those are the numbers given for different ISO zones. The finding is, if we go for one centralized plant, it's going to be costly. It might impact significantly the ISO system. If we go for kind of distributed solutions, it's going to relieve the issues related to the transportation. And for this reason, we did also the distributed kind of analysis. This diagram here shows, the distribution of the number of hydrogen generation plants needed to power each transit network in the province based on our optimization models. And as I mentioned, there is a trade-off that is noted between centralized versus distributed hydrogen production. And I'm happy to answer those questions when after I conclude my presentation offline or via the chat. For the sake of time, I conclude in here, and thank you for listening.
That's great. Thank you very much, Hani. We really appreciated that. And as you mentioned, we will save the questions to the end. I think there's a lot of interesting information in that deck you presented, and I've definitely got a couple questions for you. So we will now transition to our second presentation, which will be Dr. Ali Tariq, and the Professor of Curriculum Developer, and Sandra Munez, Project Coordinator, Applied Research, Innovation, and Entrepreneur Services at Centennial College. I will now pass it over to the two of you for your presentation on the optimization of hydrogen gas cost reduction techniques for transit agencies in Ontario. Thank you.
Thank you, Matt. Thank you, everyone. Happy to be here. Trying to pass the screen, but not working. Perfect. For today's agenda, we have introduction of the team members who participate in the project. We are going to talk about the project scope that was divided into background research and analysis of the hydrogen technology, the results of this phase. We have model optimization and the results, also conclusions and industry impact, and some questions. For the team members. So for the technical side and the technical guidance, we have Dr. Ali and we have Professor Sig there. In the management part, we have myself, Sandra Munoz, and we have Gustavo Cisneros. And also we have 4 student researchers, Olga, Shaheen, Joanie, and Matthew. For the project scope. So this project aimed to develop an optimized cost reduction technique by replacing traditional fuels for hydrogen fuel being used in urban transit agencies. The methodology that we follow was to define the objective, which was replacing the traditional fuel, and get to know what were the function constraints. After that, we did identification of that decision variables. So what we did is we collect real life data and we analyze this data to different variables that were associated with the production, the distribution, and also the consumption of replacing that hydrogen in the urban transit network. After that, we create a model formulation. This model formulation established on cost models. Again, the cost models were checking what was the consumption attributes during the hydrogen production. And lastly, we do some testing. We did some testing and validation that influence these parameters that I just mentioned, considering wheel-to-wheel components. So here, Professor Tariq will continue with the technical part. You are on mute.
Still on mute.
While Professor can get access to his audio, I can continue. So as I say before, we did a background research and we did a hydrogen analysis of the technology. So we analyzed 3 different main factors. The first one was the production, where we compared the steam, methane reforming, and the electrolysis of the water. We did some analysis with the CSD, considering that we were planning to generate 1,000 kilograms of hydrogen per day. We use information based on the year 2022. And for our model, we start in 2021. This project was created in 2021, so that was our start point. Also, we consider that we have a plan life of 20 years. So we were considering that urban agencies, we will have 20 years of the plan. Now it's working, Professor. You can continue with the headset set.
It's working?
Yes.
Yes.
Okay. Thank you very much. My name is MD Ali Tariq. As Sandra said, I'm the principal investigator of this project. I had experience with hydrogen fuel cell and hydrogen technology. So our goal was to optimize the production cost or consumption cost and distribution cost and globally optimize these 3 things. So we did research on production. We did mainly focused on steam methane reforming and electrolysis of water. Considering the existing availability of steam methane reforming and the efficiency of the steam methane reforming over electrolysis. It is a little bit higher at least. We have chosen this time, for the time being, SMR method for optimization of our research. And we choose 1000 kg per day and 20 years of the production life, equipment life. Sandra, can you switch? Okay. We developed models for CSD, that means compression, storage, and dispensing. And we developed also model for production. And this is similar, CSD per kg of hydrogen, capital cost, operation and maintenance cost per kg, other variables. And for production, we developed models for capital cost, total, cost for per kg is capital cost, decommissioning cost of the equipments after 20 years, fixed operation and maintenance cost, feedstock cost, which is in our case is natural gas, then other costs like electricity, carbon tax per kg, hydrogen, but I think we are much lower than the 60,000 ton per hour per year to give carbon tax. So we developed this compression, dispensing, storage and dispensing model, and we validated this model later on. For dispensing, we considered initially centralized production and dispensing through trucks or other things, but considering the transport and climate and other things, our pipeline, we selected that on-site is much better. Okay, Sandra, go ahead. So this is our comparison result after real life data. The right side one is our one for Ontario, and left side was the real life data for BC Transit, Whistler fuel consumption. We can see from there the dotted lines are the temperature of throughout the year. So red one is from 2013 to 2014. The green one is 2012 to 2013, and the blue one is 2011 to. So we know the Canadian temperature still is June, July, August. It is summer type weather, and our temperature is much higher, say 15 to 20 degree. And December, January, February, it is near zero or below. So we compared, and based on our consumption research, we saw that as BC Transit real life data is, you can see that during summer it is lower, and during winter it is much higher. This is because, and we got the same thing on our research, which is Ontario based. This is because during summer we identified that HVAC of the bus is much higher in comparison to other consumption criteria. So HVAC compares the infiltration, exfiltration during winter and summer. We analyze the thing, bus shell, opening time of the doors, stoppage, frequency of the stoppage. We took data on those things, and then we validated the model on the right side with our model. Okay, go ahead, please. We have chosen 10 routes of the existing bus routes of TTC Transit, and we analyzed on the basis. We took the real life data. Our students rided the buses and got the real life data. They calculated the bus stoppage and door opening time, passenger weight. Also, they calculated how many passengers got in. On the basis of that, they said average daily consumption in a year with our model. We calculated those things on the right column, 3754. We have chosen Progress Express, Brimley, Highland Creek, those things, those bus routes we have chosen. And we got the 10 bus route data. Okay, go ahead. For consumption, we identified that consumption, if we could reduce, because production and distribution, maybe it is existing one established fact, but consumption, we could do some research. We did a lot of research on route infrastructure, the first one with RGs and other existing softwares. We analyzed weight of the passenger impact on consumption. We analyzed the uphill, downhill of the existing route, which we said grade later on. We analyzed the temperature effect, yearly temperature effect. We analyzed those things, and we saw that if you can optimize those parameter decision variables of the local optimization on consumption, it could be lowered, and we validated those things with our model. Continues on the. This is our monthly total consumption based on our data. So we saw January, February, March, as you saw before in our other graph, that March, April, May, the consumption is lower because of the mainly the HVAC things. HVAC, and also it could be with the passengers, but mainly HVAC, door opening timing, infiltration and exfiltration, and October, November, December during cold climate conditions. So consumption is higher because door opening, door closing, and there is say exfiltration. Okay, continue. This is our real life data for production hydrogen cost, and station dispensing capacity. So we saw this from this graph that if we increase the production or station dispensing capacity, you see that it is slope is little bit down when it is 1500 kg per day. We already checked how much kg per day would be the consumption. We saw that during peak period it could be 1400 something kg, and during off peak it is during off peak of the day it is around 400 something kg per day. So, but we identified that more dispensing or more production of hydrogen or more usage of the hydrogen, the production cost goes down. It is natural. Okay, right. This is the cash flow analysis. We have chosen right side in the middle column. You can see we have chosen a lot of parameters, and we analyze the cost on the right side with the bar graph. And we saw that it is not our one. It is actually National Renewable Energy Lab, but we use these parameters to validate our models also. So we saw that existing cost of hydrogen is in USA, it is 10.29 per kg of hydrogen. Okay. And we use this data for our validation purpose. Right. In conclusion, we can say a couple of things to improve our things. We have chosen steam methane reforming is preferred over electrolysis. For the time being, due to the availability of steam methane reforming and production commercially available, we have chosen this one. But in future, we can go to electrolysis, that is a different story, or renewable electrolysis, we can do renewable energy. On-site production is preferred over centralized. I said already because of the transport system, the climate conditions, and on-site production is better. We have chosen STC as our real-life data collection. STC is one of the hub we can choose for production in STC and dispensing it to nearby, compression and dispensing it to nearby stations. Similarly, like STC, we can select some other hubs and distribute locally with the hub. For the selected 10 routes, an average hydrogen production of 902 kg per day, and, oh sorry, I did a mistake, 400, not 400, 90 kg per day during off-peak, and peak hour is 1421 kg per day. Peak hours are from morning 9 a.m. to 3 p.m. Consumption is higher during this peak period. It's natural that passenger is getting in, passenger load is involved here. And also consumption, door opening, door closing time, and the stoppage frequency is also higher there. Factors such as the number of stops, road grade, and temperatures into others. Road grade. I'm very much interested about road grade because if we can make the road in a way that in long run, it would be very helpful, say, not uphill, downhill, but it is a flat or lower grade, then we can reduce something. We can reduce a lot of fuel consumption. How to improve efficiency? We didn't do powertrain consumption fuel. That is not our beyond our scopes, but it could be done. The power consumption due to powertrain of the actual mechanical systems. Improving bus specification, maybe bus weight, composite material we can use for the bus itself. AC system, we can have high efficiency AC in future. Mississauga, Brampton, St. Catherine, Oshawa, Newcastle as possible future terminals. We could, as I said, as Scarborough is our hub, but we could set those places as hub for the local production of hydrogen. Implementing GTFS and GPS data. We used ArcGIS and Python, some other things, but we could use high-level softwares to get more information on tactic power consumption for route optimization. Thank you very much. In short, this is our thing, and we have given 12 minutes, so we could not tell a lot of things. Okay, thank you very much. And any question, answer, I will let him.
Dr. Tariq, Dr. Muniz, great presentation. Thank you very much. I am sure there are a lot of interested parties on the line that would identify in that last bullet point of your presentation. I'm going to hand it back over to Vince for a quick message from our sponsors as we move into the break of the session today. Before we do that, I just wanted to highlight two things. One, there is the open Q&A chat opportunity. Please enter any questions you have in there, and we'll be able to address them at the conclusion of all of the presentations. And additionally, if Alan Young is within the group, and you can identify yourself with your name on the icon for the chat function, that would be great, so we can make sure to include you in your session later this afternoon. With all that said, Vince, over to you.
Thank you, Matt, and thank you, our speakers so far. We're now going to head into a quick break to give everyone a little bit of a neck exercise and bio break. But before that, we'd like to have another sponsor commercial with our friends at NFI.
Lighter, longer range, better energy recovery, and smart city capable. Our most advanced electric bus just got better. Introducing the Excelsior Charge NG, our next generation battery electric zero emission bus. Safely carrying more passengers for a longer range, the Excelsior Charge NG delivers new high-performing technologies, including a new lightweight traction drive system with up to 90% energy recovery, next-generation high-energy batteries that extend range up to 13%, and advanced protective battery packaging designed for easy install and streamlined maintenance. With simplified design and better system durability, the Excelsior Charge NG offers a high-performance bus that's more sustainable and easier to operate and maintain. With uncompromising quality, fewer parts, and more recyclable components. This is how we're driving the new mobility era. This is the Excelsior Charge NG from New Flyer.
Indeed. Yep, we're
Okay,
ready to
so
rock and roll here.
We'll kick off part two, and over to you, Matt.
Fantastic. Thank you very much, Vince. So our third speaker today will be Dr. Zhangguo Li, Professor of Mechanical and Mechatronics Engineering at University of Waterloo. The presentation today will be on the development of low-cost, high-performing, and durable PEM fuel cells, and Dr. Lee will be supported by Alan Young from Ballard Power Systems. Dr. Lee, over to you.
Anyway, thank you very much. I hope that people can see my screen now.
Yes, we can see it, Dr. Lee. You're all set.
Okay, wonderful. Okay, so my talk today is about the project that we complete with Q-chip support. Is about developing the advanced membrane electrode assemblies for the next-gen PEM fuel cells. So kind of a very big title. The project team consists of myself at the University of Waterloo and Andy Sun at the University of Western Ontario. Andy is traveling today, couldn't join us, and he has a team member joining the meeting today with us. The industrial partner mainly is the Ballard Power Systems in Vancouver, and Ellen will be helping us for the presentation. And Star Power on System, which are doing the extension of the work. And so the project basically starts with Q-chip ANSYS CID support, and then my text joining in. And the project was approved in 2018, officially announced in early 2019, February 28 to be exact, 2019. And the project supposed to be finishing, and we got a little bit extension due to the COVID, situation, lab shutdown on campus. So that's where the things are project based towards the end. So if we're looking back to our original proposal, our objective was to develop low cost, highly performing and durable fuel cells. So that's the kind of ideas. Since for mobile application we have in mind, so we like the fuel cell developed to have a high power density operation as well. And that's based on the two kind of, statistical analysis data coming out of US Department of Energy, that the MEA basically consisting of, this part. So cost-wise, it is the majority of the cost in fuel cells. But for mobile application, the weight and the size are important. So if we look on the size and weight are majority due to bipolar plates. So these become the two focus of our initial project kind of idealization. So we're looking on the catalyst built into the MEAs. And then we'll look on bipolar plates and build into short stack. This is kind of multi-year bigger project. So what end up to be with Q-chip was that we end up with catalyst as a phase 1. So as I mentioned, that was approved in late 2018 and announced in early 2019. So that's the case. And currently we do have a separate initiation on bipolar plates. And we're hoping that this will be our next step direct following phase 1. So that's the kind of general idea or status are. So in order to improve, the catalyst activity as well as stability, that a number of things could be done. And most of the thing which coming down to the two approaches we are taking in this particular project. One is using atomic layer deposition technique. The idea arising from the understanding that in fuel cell electrochemical reaction leading to power generation, it's a catalyzed surface reaction. So what's important surface area, not to the mass, but what's important to the cost is the mass. So therefore, that you could put the precious metal catalyst on the surface of a catalyst media, and only the precious metal catalysts are kind of put as atom by atom lined up on the surface that reduce its mass loading, but still have a large surface area loading such that it can facilitate the electrochemical reaction. And another kind of approach to it that make a simpler but more engineering application kind of friendly approach is that we know that for a given amount of mass, spherical shape gives us the minimum surface area. So if you make any other shape other than spherical, for the same amount of mass, you get the more surface area. That's one angle. Another is that if you have a shape of catalyst particles, at the edges and the corners, you tend to have most of the structure, dislocation or imperfection. That's the location actually can make, the catalyst more catalytically reactive as well. So this was the original ideas. And then just to be a bit more schematic, this work was done at the University of Western Ontario for atomic layer deposition kind of technique to be used to, modify or fabricate catalysts, so that this approach, can provide a precise control at the atomic level where you want to put the catalyst atoms, for example. And then since you can control at the, at the atomic level, so at a larger scale, you will see the catalyst structure or microstructure look very uniform. And the technique can use at the low temperature, even, room temperature. And this technique can be, applied to a large range of materials. So that's very nice. And so if you want to look at the kind of general idea, basically you have a heater like a furnace, and this is your target surface. And then you have a two system coming in that will provide, the vapor pulse one here that can deposit it, as you see that on the surface of your, targeted surface where you want to deposit your kind of monotonic atoms. And so in this process, you could basically increase manufacturing process, making more efficient and higher productivity. And you can have a area selective deposition, meaning, where you want to, like in this case, there's one type of atom, another which is the platinum atoms. They can selectively deposit on a target surface, and or you can make a little more larger scale, so you can look on the nanoparticles. Oh, what happened? Okay, so in that way you see platinum, ruthenium, and different type of atoms can be selectively deposited at the right location you need to make the catalyst, more functional and more stable, meaning have a longer lifetime, have the better catalytic activities, and so that you can making a various type of, complexity of these structures. I'm not going into the details, basically, so that a single atom kind of modification can be also used, to modify the existing, for example, commercial catalyst. And you can do the comparison. For example, these are like a platinum support carbon commercial catalyst. These are niobium kind of atom being doped. So what you are seeing, this is the platinum on a carbon support surface. And here's where niobium being doped, especially in the corners around here to make platinum particle more stabilized onto support structure. So that if you're looking on that
Sorry, Dr. Lee. We're having some issues on the front end with some people not seeing your screen. So do you mind stop sharing and I'll share your screen for you?
Okay, yeah, seem to be working. I'm just going to continue until they stop me again. So what you are seeing is that from this electrochemically active surface area and this the mass activity, the niobium atomic deposition increases. These are the durability cycles compared to the commercial catalysts. These are the doped commercial catalysts, and their mass activity, electrochemical active surface area all improves basically. So that's the general ideas. And in terms of nano-shaped platinum-based catalysts, what we're trying to do is first we have a kind of carbon support. We do some sort of functionalization or treatment as well as nitrogen doping. Then we put all ingredients into one pot, like cooking a soup, everything in one pot. And at the end of the action, you got the catalyst you need. So it's a simple one-step synthesis of catalyst, easy to scale up, and you could have a cheap, manufacturing process. And I don't want to go into details, but you can see that the catalysts have improved activity and making a catalyst layer. We can look on resistance to the permeability to mass diffusion, essential resistance to mass transfer, the reactant getting to catalyst surface for reaction. That particular configuration has a minimal resistance. And in terms of catalyst, characterization results, I'm going to leave in for a second. And then when making the actual, using this catalyst, making the MEAs, we're getting a very good performance. So if depends on who you're talking to, US Department of Energy, their original target getting 1 watt per square centimeter, and the newer target of 1.2 watt per square meter, and we can far exceed that. So that looked very promising. And so we turn over the both Western Ontario and University of Waterloo, the catalyst developed in 2 institutions, and to our industrial partner and financial supporter, that is Battery Power Systems, and they done their own kind of characterization measurements. So I'm going to turn over to Ellen. Ellen, so if you could just take over these slides for the work you've done at your place.
Thanks, Dr. Lee. It was a pleasure to work with both Western and Waterloo and Dr. Sun and Dr. Lee on this project. So here's a brief. We kind of took what they developed and tried to put it into a small fuel cell, similar to a little bit of the work that Dr. Lee showed. So this slide here is reviewing the Western work. It's just on the left, it's replotted a little bit the results that they had found at Western. So here you can see a platinum cobalt baseline in red, commercial catalyst, and then they've decorated it via ALD with niobium oxide. And so it's been treated. And you can see the durability of these catalysts are quite a bit different. This was quite exciting to us, and we wanted to evaluate. So on the right is an in situ MEA evaluation. Again, it's small scale, but we can see a similar effect on durability, where at the beginning of life, we see very similar performance. So the treatment did not alter the activity or have any kind of negative impact, but there does appear to have a durability benefit after it's gone through a number of cycles, and the cycling and the polarization details and conditions on the top right corner. So this is a promising result, and we're looking. We've got a few more samples. It certainly needs to be repeated and studied in more depth. And we've actually just received samples a few weeks ago to continue outside of the project. The project's completed, but we're continuing to evaluate samples and trying to develop the understanding here. In our next slide, we looked at the Waterloo catalyst. You can see on the left-hand slide is a graph an ex situ evaluation via RDE, where we looked at Dr. Lee's platinum on CG carbon support. And then we compared it to a couple other baseline materials, a low surface area catalyst and a high surface area catalyst. You can see the Waterloo's catalyst, the platinum CG, is outperforming at BOL, both of the commercial catalysts, and it had improved durability over the low surface area catalyst, as what Dr. Lee had shown. So is doing quite well. On the right, unfortunately, when we put it into our in situ MEA evaluation, it did not perform very well. So it was the platinum on CG support is in the red or purple color, with the baseline catalyst, commercial catalyst being in the blue. Now, this shouldn't really be a commentary on the catalyst itself. Dr. Lee had shown very good performance, and we saw this in the ex situ results. What this highlights is the need for much more work and understanding on the scale up and processing of the catalyst. So I think it's just based on the processing methods that we used, we created a layer that underperformed. And so that would be future direction, is to understand varying techniques. And the technique we used was different than what Dr. Lee had used in his lab. So we have ideas of where we could go to improve this. That's all I'll say for now. I'll turn it back to Dr. Lee for the rest of the presentation.
Thank you very much, Alan. We're almost done anyway. So this is just a summary, maybe no need for me to read line by line. Basically, that it showed this new catalyst has a potential to be incorporated into actual fuel cells, but the fuel cell manufacturing procedure may need modification because the existing technique are more suited for the existing material. So if you have different material, you need to adapt to the material characteristics. So that thing being said, so we're looking forward to our next phase of the project, basically. Okay, so I'll stop over here and thank you all very much.
Thank you very much, Dr. Lee. And with that presentation, we conclude session A, and we will now transition to session B, which is entitled Finding Efficiencies, Optimizing Energy Use and Reducing Greenhouse Gases in Fossil Fuel Systems for Bus and Truck Applications. For this presentation, we'll have Dr. Eric Blaze, Director of Applied Research and Innovation at Centennial College, and his presentation today will be Applied Research in Battery Storage Systems for Increased Fuel Efficiency in Trucks. Dr. Blaze, over to you.
Thank you very much. So as opposed to the previous presenters, which were university professors or college professors in great part, I'm the Director of Applied Research at the college, and I'm responsible for industry college collaborations in aerospace, advanced manufacturing, and once in a while in energy systems as well. So next slide, please. All right, so for those who don't know who don't know about Centennial College, we're one of the 24 colleges in Ontario, and we are mainly located in the eastern part of the GTA. So the eastern part of the Don Valley for 4 of our campuses. So our Ashtonby campus, our Morningside campus, our main campus, which has a Progress campus. So if you're just driving on the 401, you might see this in Scarborough. And then the Story Arts Center, which is kind of the Danforth neighborhood. Our newest campus is the Downsview campus. That one is not in the eastern part of Toronto. It's in Downsview Park, really in central. And it's it just opened in 2019. It's the Bombardier Center for Aerospace and Aviation. And it's really our latest jewel that we have. Next slide, please. So as this previous slide said, we have 25,000 full-time students at the college, which is a fairly large student body. And we're able to tap into these students to do applied research projects. The students study in 7 different schools that are at the college. mainly for our applied research collaborations. I would say the students that come for our research projects are the ones from the School of Engineering, Technology, and Applied Science. That school has about 5,000 full-time students. Our School of Transportation is getting more and more involved in research, especially related to topics related to Kutrick, and you'll see more stuff later in my presentation. The business school as well, when there's business cases to be made, an analysis from that point of view. So why the college does applied research is really for experiential learning. So students learn a lot in class, get their mainly technical knowledge, but then when they work with industry partners, they really refine that knowledge and develop a lot of soft skills. So we've done applied research at the college here for about 20 years. And the next slide, we kind of like show that what we've done and what we've focused on. Next slide, please. All right, so really the applied research at Centennial College started really in our School of Community and Health Studies. So really in our nursing program, where applied research and treatment methodologies was central to their curriculum. But in the college sector, applied research has grown over the past 2 decades. And at Centennial, that School of Nursing and our health technology is still very much central to what we do, and has grown substantially. So we are now rebranding ourselves as Centennial Innovates. That's our Applied Research, Innovation, Entrepreneurship Services department. And we have different areas of strategic importance. So definitely advanced manufacturing, aerospace, transportation, energy, data analytics, social innovation, and WIMTAC, which is our Technology Access Center for wearable mobile technology access center in health. So as you can see in the roadmap here on our left, we've grown our applied research expertise over the past 20 years. And we've done energy and renewable energy since about 2012. So literally 11 years now, or 12 years almost, like in doing this. And everything we do is mapped against the UN Sustainable Development Goals. So all the research activities that we do are mapped against those. So for those, really the applied research really is developing new solutions and new products for real world challenges. And we're proud at Centennial to be the #1 college in Canada for offering paid applied research internships. This is really what we're strategically focused on. And the next slide, please. And we really try to bring that with industry college partnerships. Of all the programs, we have a lot of programs at the college. And I just want to highlight one in particular that is part of our School of Engineering, Technology, and Applied Science. It's a program that's called Energy Systems Engineering Technology. This is a 3-year program with an optional co-op. So some of the research work, definitely the students can do in their co-op term, but they learn a lot of things that are relevant to energy management, energy systems, and also that is applied to, we lost the slides. All right, thank you. So as I said, in this program, students learn about energy optimization, usage reduction, energy storage, microgrids, but also all the different systems and different components that go into a systems and how to optimize those. So these are the students that we tap on the shoulder to really do these research projects in energy systems. And I want to highlight a few projects for the next slide, please, that these students have worked on with faculty members. So the first project I want to highlight is a project with Toronto Hydro and eCamion at the time. So Toronto Hydro has a mandate, amongst others, to reduce its greenhouse gases. And one of their sources of production for greenhouse gases is their service trucks. So these are their underground service trucks that go to different sites to repair underground cables in the distribution network. So this was they were looking at how to reduce their greenhouse gases from when they use these trucks to go to different places, but also to power the tools that they have in these trucks to do their work. And we worked with them to evaluate 3 different types of trucks. So trucks with no energy or I could say fuel reduction mechanisms. They had trucks already in operation that looked at lead acid batteries and a system that was commercially available that they already had in a few trucks. And then eCamion was proposing one of their eAPUs to look at reduction of greenhouse gases. Now, our students, so essentially this project is one faculty member who unfortunately couldn't make it here at the presentation today. We had 3 students and 1 project coordinator. And this project is literally about 6 months long, where we assess the fuel consumption of these trucks, but also the whole energy systems, where we collected data at different points in the energy system that was installed on board, and compared the fuel consumption of all the different trucks, and also the return on investment. At the conclusion of our analysis was, the IP that was generated and all the analysis was given to both industry partners, and then they're able to make financial or decisions on how they want to go about in developing their different solutions to reduce their greenhouse gases. What we found in this project is essentially the return on investment was 2 to 3 years on the batteries that were proposed by eCamion at the time. Next slide, please. This is somewhat similar, where it's a different industry partner. This is microgreen solar. We had a project that lasted a little bit over a year. Same thing. Actually, we had a little bit more students here. Longer the project, sometimes there's a student that they graduate, and then we have to hire new students to continue the project. But this is looking at solar energy generation and then storing on board to reduce the greenhouse gases for a truck. And the students developed a model to look at what were their energy requirements. They simulated that on software, and then developed a prototype at a lab scale, but also started looking at it on a truck and installed some of those components on a small diesel truck to validate some of these components. So this project kind of wrapped up fairly quickly, but did show that there was huge potential in using the solar panels to reduce the consumption of gas for generate electrical to power the electrical systems on the truck. Next one, please. Now I want to all right, so now I want to highlight an opportunity for additional industry partners to come and work with us. We recently received a Mobilize grant from NSERC. It's $1.5 million over 5 years. And the major themes that we focus on is electrical vehicles, but also low carbon mobility and automotive and hydrogen, and also aviation, mainly repair and overhaul of aviation. So these are what we have funding readily available to work with industry partners on these topics. And we have one project that just started not too long ago that is looking at again kind of energy optimization, energy use, and reduction. It's a truck. It's also for reducing energy consumption in a refrigerated truck. And that this project just started recently, utilizing one of our trucks that we have at the School of Transportation, as well as students from mechanical engineering programs and the energy systems programs. And that kind of summarizes, next slide, kind of concludes my presentation for today. And thank you very much for your attention.
Thank you, Dr. Blaze. We appreciate it. At this point in time, we will be transitioning to the Q&A portion of today's seminar. I welcome all of the presenters and panelists to come back on camera, and we will start to go through some of the questions. The first two will actually be for the entire panel. So when everyone's back online, we can jump right in. I can see, Hanny, you're in there. So let's start with you. Question for everyone to think about is, how do we address the public optics of safety issues related to hydrogen? Hanny, why don't you kick us off? What are your thoughts?
Well, yeah, it's a quite challenging question. I know it's everyone has concerns about the safety for hydrogen, especially when it comes to the mechanisms of hydrogen storage and transportations. Yet, safety, standards to be definitely, developed in the coming years. And there are many factors that, might impact how safety is going to be developed. Among those factors are the mechanism, again, of, the storage and transportation for hydrogen. Now we talk about the fact that most of the hydrogen, it could be just, a significant portion of it to be produced in the form of gaseous using the water electrolysis. And when it comes to the mechanism of the safety, we have to ask a few questions. Are we going to be more centralized or more distributed? That's a factor that going to impact, the development of the safety standards. And the second is in terms of the storage, if we go for a more kind of seasonal storage, again, the question is it going to be in a form of a compressed gas or liquefaction or liquid organic hydrogen carriers? And again, it's, safety is going to be addressed based on the right solution, but the problem is quite complex because there are also other techno-economic aspects that need to be taken into consideration. So the right solution in terms of safety is yet to be determined, but at the same time, we need to look into the techno-economic aspects related to it.
Fantastic. So it sounds like, just to summarize, safety standards and how it will be stored and transported versus localized or decentralized production methodologies.
Yeah,
I will pass it over to Sandra next. What do you think, Sandra? We have her on mute there. That's okay. We'll wait for that one for her to come back on. Dr. Lee, what about yourself? What do you think how do we address the public optics of safety issues related to hydrogen?
Well, first of all, anything with energy content, it can be a risk. And typically industry develop, codes and standards. As long as codes and standards are being followed or respected, usually no problem. If you're looking on historical data, hydrogen actually is safer than gasoline or diesel. There's a serious safety test go back as early as year 2000 in the United States. For example, one hydrogen fueled vehicle and one traditional, gasoline or diesel fueled vehicle, they go a crash testing because gasoline, diesel liquid are heavier than air. They usually a crash will cause a leakage of fuel on the ground and burning upwards and burning the vehicle. And often the crash deform the vehicle and occupant may also get hurt and may not be able to get out of the vehicle quickly. It is subsequent fire that causing the fatal damages. But if with hydrogen, you could have a smash. The hydrogen is so light compared to air, it's only a fraction of it. So that the once you will take hydrogen way high up in the air, burning occur in the air, not around the vehicle, so that it actually safer. It depends on which angle you are looking at it.
Great response. It reminds me of someone in the hydrogen safety business once said to me, they said, there have been 0 challenges with hydrogen refueling compared to the internal combustion engine. And if today's standards, we were to bring forth an energy modality that had refueling between your legs at a gas station that you're driving on, and you could be potentially smoking at the same time, it would not pass. So it's very interesting to see the internal combustion challenges, if it were introduced today, compared to the same challenges that we face with hydrogen. Great response. Thank you, Dr. Lee. Dr. Muniz, do you want to chime in?
Yes, sorry, I have problem issues. So I think we have to consider the same factors that we have with the other fuels. So it's important to educate and train people on how to use this kind of fuels. Also, we have to improve the safety standards and regulations, because I think it's a lack of how to transport properly the, for example, hydrogen fuel tanks. So we have to ensure that our regulations and all the standards that involve safety are taken in place to ensure that it's safe to manage hydrogen.
Fantastic. Thank you very much. Dr. Tariq or Dr. Blaze? Dr. Blaze, I see your hand up.
Yeah.
Please jump in.
Yes, I can talk about something that we did at the college very many years ago, where we had a research project that we wanted to store hydrogen at the college, and people within senior leadership vetoed any activity that we wanted to do. So I have to second Sandra's assessment that education is really important. I think there's perception that there's this danger, and it might not be entirely realistic, and that's where education can address some of that. I mean, apart from the answers the other panelists have also exposed, but I think education is number one from my point of view.
Okay, Dr. Lee, it looks like you have a rebuttal.
Now, I just want to add on, knowledge is really important. I give you an example. I think in Munich, Germany, a number of years back, they have a refueling station planned in somewhere in the middle of cities. And after safety assessment, they turned down the request to build a gas station. However, what they eventually approved was a hydrogen refueling station. Just if you know the right knowledge, you can make the right assessment for it.
And I think panels like today are the essential for us to get that information out, and hearing from the experts here today has been great. Dr. Tariq, do you have a final comment on that question?
Any new innovation people think it's unsafe, like nuclear and other things, but with code and standard and regulatory bodies, it could be maintained. The safety could be prioritized. So I think hydrogen is inflammable, very highly inflammable, but we have to take the precautionary measures and public awareness, as Sandra said or Blaise said. Yeah, that can be possible. I did a research on intercombustion engine, hydrogen fuel intercombustional engine, and there was a problem in the IC engine that it does pre-ignition because of the previous firing. So I propose that hydrogen could be pre-cooled so that the kindling temperature should be lower when it gets inside the cylinder. That is IC engine. That is not with fuel cell, but people should be aware and educate about the usage of hydrogen.
Fantastic. Thank you very much from everyone. So to overcome the optics, we need to work on unified safety standards around storage and transportation, understanding the education component, and realizing that as new technologies come to market, they take time to work through and overcome those legacy challenges that we see with hydrogen. I think I see some nodding heads, so that sounds pretty good. Thank you very much. My next question, and this is a great opportunity to build on the idea of education, how do we get governments engaged to act on the opportunities that hydrogen presents for decarbonization? Dr. Blaise, I will throw that one to you first, because I can see that grin. You look like you've got something great to add.
Well, definitely, I can talk. I don't know if how much I can say, but the School of Transportation, I didn't mention everything that we have at the School of Transportation during my slide deck, but we have the biggest school of transportation in the country here at Centennial College. And we see hydrogen as a key element for decarbonization of heavy equipment at the school. So we are definitely moving forward at a strategic level for future of hydrogen in our School of Transportation for everything that is, trains, heavy equipment and all that we teach the maintenance and repair of those equipment at the college. So it's something that we plan for the future. And when we do strategic investment in new campuses and new facilities, we have to plan for that accordingly, because we plan for buildings that will last, for the next 20, 30, 40 years. So hydrogen is part of that vision for us.
Fantastic. And Atura Power is here to help you with all the hydrogen you need. So I'm sure we'll have many conversations afterwards. Henny, I saw your hand up. Did you have some insight you'd like to share?
Well, absolutely. Well, I mean, the entire world is moving now to applications for hydrogen, and particularly for the hard to decarbonize sectors, right? So it's not necessarily to be applied for transportation specifically. I think, the applications of hydrogen is way more than just application for transportation. We see, the potential of application for hydrogen for steel making and for other, fertilizers and other potential applications. That's, I guess hydrogen could definitely play a significant role in terms of the decarbonization and reaching to the target of net zero by 2050. Some good news, we just, I guess in the past maybe months or two, US, just unveiled their hydrogen strategic plans, followed by many other, countries who have already, unveiled their hydrogen strategic plans or strategies over the next decade or two. US, as you know, they have in the IRA, the Inflation Reduction Act, potentially, subsidize and compensation or credits for hydrogen innovation. We just see, that our Ontario government here, they have a good funding for Hydrogen Innovation Fund that is administered by the ISO. And I guess all those kind of initiatives from the government and hopefully support also for researchers like ourselves could definitely, take that to the next level.
Fantastic. Does Dr. Lee or Muniz or Tariq, do you have anything to add?
Yeah. I can feel that hydrogen is the most promising energy carrier. We can produce hydrogen with solar energy, solar electricity. So production provides the most carbon generation for hydrogen, say carbon leakage or carbon intensity. So I saw that Canadian government few days back, during my time it was not there, Canadian government announced that 15 to 40% tax rebate on hydrogen production based on 0.75 kg per kg of, or less per kg of hydrogen. They will give 40% tax credit. 0.75 to 2 kg, they will give 25% tax credit. 2 to 4%, they will give 15%. Above 4%, they will not give. So government is encouraging. So if we cope up with the safety and other thing and production of hydrogen with less carbon, then hydrogen is the most prominent energy, would be the energy carrier in future.
This is a great point, Dr. Tariq, and I'm going to ask you to hold on to that point because I have a very specific question on your presentation that will touch on the investment tax credits rolled out by the Canadian government. Before we do that, let's swing over to Sandra for her quick input here. Sandra?
So to sum, I will say collaboration is the key. So we have to work between industry, we have to work with the government and educational institutions. We have to help the government to realize that education and current industry kind of we align with what are the goals of the government right now to get greener, right? And also with the education institutions, take the opportunity to train our workforce and make sure we can both all point to the same direction. So collaboration is the key.
Fantastic. Collaboration, education, and investment tax credits for new technology really seem to be the summary of that, while ensuring that the institutions today are preparing for the transition tomorrow. And Dr. Blaze will be looking to you for that in the coming decade or so. We have a question from the audience that I might try and take on myself, and this is: Canadian utilities are not investing in transmission as much as the demand for hydrogen production is indicating. While in situ production may have local advantage, it may not be practical to find local capacity to scale hydrogen production. And if there were any comments and feedback on that. I think one of the challenges from our perspective at Atura Power is ultimately the transportation of hydrogen. And ultimately it's transportation and storage of hydrogen. And we believe that this is one of the biggest challenges and simultaneously a wonderful opportunity for the entire hydrogen industry. So when we look to the future in Ontario, I think that hydrogen will develop around localized hubs, specifically touching on transportation aspects. But to Hanny's point is that it's not just focused on transportation. I was running some numbers really quickly here at the back of the envelope. Transportation and heavy duty transportation, pardon me, and industrial processes account for 55% of Ontario's greenhouse gas emissions. And if we were to say that hydrogen could even challenge half of that in a localized opportunity, it leads for this wonderful runway to develop localized hydrogen infrastructure to drive down the cost and long-term start to see hydrogen grow beyond those localized hubs. When we look at it from a national perspective to this audience member, I also think that it's very important to realize that hydrogen production pathways are very much determined by the localized geography of the regions that it's produced. In so much as to say Ontario has 58% of our electricity is generated from nuclear power and about 18% from hydro, with another 8 to 10% from renewables. So we're very well suited to produce low carbon intensity hydrogen from the grid. Similarly, BC and Quebec are very strong in hydroelectric production and have an opportunity through interruptible rate pilots to produce low carbon intensity, low cost hydrogen. However, we remain challenged in other provinces across the country where you're going to start to see blue hydrogen being more predominant in Alberta because of their underlying geology and their ability to store carbon underground through CCUS. Conversely, on the East Coast, where the entire grid is principally run off of oil and gas, is that they are now having to erect turbines to produce hydrogen, low carbon intensity hydrogen in places like Nova Scotia and Newfoundland. So to the point is, it will start locally, but it will grow across the country. And I think that's something that we have to remember, is that it's not going to happen overnight. And as Dr. Tariq said, is that new technologies take time. I will pause there. Dr. Tariq, you have an add-on. Please jump in.
Yes, any new technology, public don't accept. Even the gas engine, steam engine, they didn't accept before. So we have to educate the people and what's going on with hydrogen, how it will help in future, all, I think, about to zero carbon technology, because we can produce electricity from the nuclear, from the solar, from the wind, from the tidal wave and other things, and harness those things for hydrogen production with electrolysis. So we could switch more or less towards zero carbon in future. I'm very optimistic about that one. And people has to understand these things, that they are damaging themselves by using, by emission, carbon dioxide emission. So I think in future it would be great. And our government just last March, they announced the whatever I said, 75.75 below 40% tax credit like that. So government is coming up, and manufacturers should come up with new technology to harness the hydrogen, like in the car, and phase out the gasoline. Yeah.
Yeah, and you raised a really good point. I think the governments are doing an incredible amount to stimulate hydrogen production. However, one of the challenges is that the timing of it and the investment tax credit and the Inflation Reduction Act was announced in August 19th of 2022. Well, we're approaching October of 2023, and we don't have an understanding of the implementation process for the Inflation Reduction Act. And similarly, I believe that is impacting our ability to understand the implementation legislation of the investment tax credit here in Canada. So I agree that it is coming. However, for large-scale capital deployment decisions, everyone is waiting on the sidelines to understand the implementation process and what those investment tax credits will actually result in. And we're seeing those challenges specifically with Section 45V in the United States, which is there's a lot of discussion around the idea of additionality, deliverability, and matchability. And until those challenges are solved, I think that you're going to see capital waiting on the sidelines before it's deployed so that they understand the long-term viability of these tax incentives. Dr. Lee, I will throw it over to you for the final response here, as we've got to close up at about 5:02. Please go ahead.
Okay, I'm trying to looking at a slightly different angle in order to promote hydrogen in Canada for implementation. Because Canada have a strong oil gas industry and often touted that the oil gas industry and hydrogen kind of competing with each other. That can be actually an opportunity for oil and gas industries. Because traditional, steam reforming approach creates CO2. CO2 need to be captured, stored, and somewhere these are the costs and all kind of things. But if you convert like a methane into a standard chemical procedure called thermal cracking, you're produce hydrogen and solid carbon. Solid carbon is a valuable chemical material you can sell for additional economic gain. So in that way, oil gas utility company can join in to promote incremental hydrogen. That's the one angle I'm kind of looking at it. Another, we're talking about green hydrogen. Green hydrogen at the moment is just the cost because they use expensive precious metals. And also the capacity for producing green hydrogen not there. But if you're using hydrocarbon, making the solid carbon and hydrogen gas, then you don't have CO2 issue in the first place. And another thing I really want to mention that we talked about so much about different color of hydrogen, but in Canada, we have great potential for one color that have not been mentioned, which is called white hydrogen. White hydrogen, basically what it means is that talking about, in the universe, how Big Bang created the universe, hydrogen being the first, element being produced in the universe, and the universe has the abundance of hydrogen, about 74%. And then there are these, geologists talking about how the solar system being formed, that, they capture a lot of these gases into forming the solar system. So deep in Earth, there's the hydrogen kept inside. And now it's discovered on Earth in a few places like French Alps and in Africa, Mali, someplace in Russia. Canada have not done any exploration. I'm sure if we can find in Russia, Canada should have a lot of those things. So hydrogen is not a secondary energy carrier, it's a primary energy resources.
Absolutely. And the naturally occurring hydrogen is something that I think a lot of people are keeping an eye on. And the methane pyrolysis, which is the element you spoke to about carbon black as a byproduct, is something I firmly believe the oil and gas industry is looking at because it has that base molecule. Anyways, I think this is a great opportunity for us to put a pause. There's definitely a lot of questions still to be answered, a lot of great conversation to be had. And I want to thank all of the panelists. All of you really are on the frontier of the energy transition, and the work that you're doing and the knowledge that you're sharing has been foundational for a lot of people to at least consider hydrogen as a future opportunity. And I can say that I learned some great stuff today, and I want to thank each of you for coming out and participating. With that, I will pass it over to Vince for some closing remarks.
Thank you, Matt, and thank you, speakers. You did a wonderful job, and Matt, you did an awesome job corralling everyone. If we could just go to our next slide, we're just going to wrap up really quick. We just want to show you a commercial. Perfect. Thank you. So that, if for anyone that didn't know, that's for our Zero Emission Transit and Mobility Conference coming up in a month. Did want to say special mention that there will be a hydrogen panel on that. And just a minute, I've lost my thing. There will be a special hydrogen, and it'll include the Canadian Hydrogen Fuel Cell Association. Edmonton will be there, and our most esteemed Matt will be presenting as well, I understand. So it'll be much more in depth, and we can have a more wholesome discussion on hydrogen and everything e-mobility and zero emission. I've put the links in the chat for you, and if you please visit our website, there are sponsorship opportunities still remaining. You can certainly register, and we definitely have the agenda up there. So we look forward to seeing you all there in Burlington, Ontario, close to all transit vehicles and airports. And with that, I think we are done. And I thank all our speakers, and thank you all for attending. We will share this video presentation of the whole presentation, and the presentations will be included in there, the slides. So I realize, I apologize for some technical difficulties on some of the slides that weren't visible, but they will be captured within the video that you do get. So with that, I thank you and wish you all a good day, and look forward to seeing you October 2nd or October 3rd for our last installment of the R&D series. Thanks so much.
Thanks,
Bye
Vince.
now.
Thanks, everyone.
Thank you.
Thank you.